Namaskar. Today in mechanics lecture series, I'll explain Hamilton-Jacobi theory. It is a theory, an approach to solve the dynamical systems. And basically this theory is based on the theory of canonical transformation, which I have already discussed in my previous lectures. You know that the advantage of canonical transformation was that with the help of canonical transformation, we are able to make our coordinates cyclic, and then naturally, if in any situation we can make all the coordinates cyclic, then the solution is trivial. So if I talk about the transformation, it simply means we want to transform from one coordinate system to another coordinate system. And if I talk about the Newtonian mechanics, then Newtonian mechanics, if we transform from one coordinate system to another coordinate system, then it is not necessary that you will get the same equations of motion unless and until you rotate your original coordinate system to an angle 90 degree. That means for orthogonal type of transformation only you can preserve your equations of motion. But if I talk about the Lagrangian or about the Hamiltonian approach, then in both the two mechanics, in Lagrangian mechanics and Hamilton mechanics, our equations of motion are preserved. If we go from one coordinate system to another coordinate system, then equations of motion are preserved. So ultimately, what is our purpose? Our purpose is to find the equations of motion to describe a dynamical system. You see that in Lagrange mechanics we have 2n first order differential equations in terms of generalized coordinate and generalized velocity. That is described, Lagrange is described in terms of generalized coordinate and generalized velocity. In Hamilton's mechanics, we have 2n equations, but those are first order equations, and then we find the equation of motion. And that in Hamilton mechanics we talk about the phase space, in which our Hamilton was described in terms of generalized coordinate and generalized momentum. So finally the purpose is to find the equations of motion to describe the dynamical system. But you know that, as I told you, that if our coordinate becomes cyclic, then what happens? Suppose you are having a coordinate system qi, pi and t. This is your old coordinate system, and you have changed this coordinate system to qi, pi and t. This is the new coordinate system, and in any case, and this transformation is canonical as well. This is canonical. In this case, you have one Hamilton H, and in this case, suppose your Hamilton is K. Now, if you can find that all the coordinates are cyclic, then what will happen? It simply means that since it is a canonical transformation, so equations of motion will be preserved. That simply means that for this new coordinate system, you will have delta k, delta pi is equal to, sorry, this will be for capital, pi is equal to qi dot, and delta k, delta qi is equal to minus pi dot. So these are your equations. Suppose all the coordinates are cyclic, then what will happen? Delta k, delta qi, this will be 0, and this implies pi dot is 0 or pi constant. let it be alpha I. Now what about this one? Delta K delta Pi is equal to Qi dot, means delta K delta alpha I. Your K is not involving any of Qi, which provides you that Pi is equal to alpha I. So this is Qi dot, and naturally your Qi dot will also be this will be constant, or you can say whatever expression you will get from here will be a function of, because k is a function of q and p. Q are cyclic and corresponding p are constants. So this expression is just an expression in alphas. So whatever will be q dot, this will be constant. These will again be constants. So you may denote these by beta I. So this implies q is equal to beta I t plus some another constant of integration. And now by substituting the values of q in terms of small p and q, you may get your equation of motion, or rather you may get you may get your equation of motion. So one way is, you know that with the help of canonical transformation we can do this procedure to get some k. But there is another way. Another way is that if you are able to find your new coordinates in terms of initial values of the old coordinates. What am I saying? Suppose your P is nothing but it is a function of Q naught, P naught in time. Your capital Q is a function of Q naught, P naught in time. Where what is Q naught and P naught? These are initial values of the old coordinates. Then what will happen? Then when you change your QP to capital QP, then what will happen? Finally, you will get your equations of motion in terms of initial coordinates. So these initial coordinates are working as the new coordinate, and you are getting your solution without any effort, because if you can find new coordinate in terms of initial coordinate and then find the transformation equation, that will be nothing but the equation of motion in terms of initial coordinate, having the initial coordinate also. So this is an effortless work. But what should be the approach? How can we find this type of solution? For that, Hamilton Jacobi theory is there. And how can it be possible? Suppose I say that what is our purpose now? Our purpose is to find the transformation equations in such a way, because if I want to find this type of equations, my k, new Hamilton, should be either constant or zero. Because if I say that my aim is that k should be either 0 or constant. Why? Suppose P, Q and P, old system, capital Q and P, new system, right? H is the Hamilton for the old system and K is the Hamilton for the new system. And in this new system, delta K, delta Qi is minus Pi dot, and delta K, delta Pi is Qi dot, right? These are the equations. Now, suppose I say that K is 0. This is one case. If k is 0, what will happen? This implies, because our purpose is to find pi dot and qi dot to be constants. If these are constant, it is very easy to find the solution. So, to fulfill our purpose, either k has to be 0 or k has to be constant. Because if k is 0, then from this equation, qi dot is 0, implies qi is constant. Right? From this equation, pi dot is 0, implies pi is constant. So, we may choose pi constant to be in terms of initial conditions, initial values of the port coordinate. Likewise, I may choose these to be in terms of values of values of the constant in terms of the initial coordinates. So, the same purpose may be fulfilled if I take k to be constant. If k is constant, then what will happen? Then again, qi dot is delta a delta pi. Suppose I say that k is a and a is a constant. Initially this is 0. Similarly, pi dot will be delta a delta qi and a is a constant. So again this is 0. So in both the cases, if I take either k is equal to 0 or I take k to be constant, I get my purpose solved. And these constants may be obtained with the help of initial values of the old coordinates. Now, if you visualize this simply means that suppose you have a system and that system is moving. So that system will have some initial point. At that initial point, its coordinate will be q0, p0 and time. Right? Now, the system is moving and it is traveling. When it is traveling, then the coordinate system will also move with it, but it will move in such a way that new coordinates are constant along the path. So this is the main theme. This is the main purpose, right? Now I want to explain that how or what is the advantage, or you can say that what type of generating function should we choose so that we can get our purpose fulfilled. That means, what is my purpose? My purpose is to make k, capital K, free from all new coordinates, k free from generalized coordinates. That means my purpose is to make all the coordinates cyclic. So with the help of an example, I'll show that it depends upon the selection of the generating function, that our k may or may not be free from the generalized coordinates. For example, suppose I consider the example of a harmonic oscillator. We take this example. I'm considering the simple harmonic oscillator. Then for that, I choose, it is simple harmonic oscillator. For simple harmonic oscillator, suppose my generating function is half m omega q square cot q. Suppose this is my generating function, right? Then first of all, I will try to find that what type of generating function is this. Is this f1, f2, f3 or f4? So you look at the right hand side. This right hand side involves small q and capital Q. It simply means that it is equivalent to f1. Okay. Now what is equation of motion for f1? Delta f1. F1 is a function of q and capital Q. Delta f1 delta q is equal to p, and delta f1 delta capital Q, any derivative of F1 with respect to capital Q, is equal to minus P. Okay. And the third one is that K plus H, K minus H is equal to delta F delta T. Okay. Now if I calculate this one, that means differentiate this equation with respect to small q and then put the expression for K, I am writing it directly. I'll get small p is equal to twice P m omega cos Q, and Q is equal to twice P upon m omega sin capital Q, sin capital Q. So you see that with the help of these two equations, with the help of the equations regarding F1, I get the transformation equations. Okay. Now what is my purpose? My purpose is to make K to be free from all the coordinates. Yes, there are two purposes. Now in this case, my purpose is not to make K free from any of the generalized coordinate. My purpose is to make K 0. If K becomes 0, then it is very simple, because your P dot will be constant, your Q dot will be your P will be constant, your Q will be constant, and you can get a trivial solution, right? So in previous theory, my purpose was to make K free from as many generalized coordinates as we can. But now at this stage, my purpose is to make K free from any of the coordinate, rather to make K 0, right? So in this case, if I constitute my K, then because F is not a function of time, so K will be equal to H. So if I calculate this K, then H is P square upon twice M plus half of M omega square Q square. This is Hamilton's function in terms of small q small p all coordinate, because I have to find the value of capital K. So I'll replace this small p and small q in terms of capital P and Q. So I may find the replacements with the help of these two equations, and I get K is equal to omega P. So you see, this K is not 0. This K is not constant. My purpose is to make K constant or 0. So if I do this question, the same question with the help of some another generating function. Suppose my generating function is Q, P and T. This is a generating function of type 2. You know, this is of type 2. This is minus 10 omega T upon omega P square upon 2M plus half M omega square Q square plus P Q sec of omega T, right? If this is your generating function of the same problem, then what will happen? You know that in this expression you are having something is wrong here. This should be capital P, right? In this expression you have capital P, you have Q. So this simply means that it is fulfilling the conditions for it to be F2, right? This is F2, this is F2. So I'll write the equations of motion regarding F2. Delta F2 delta Q is equal to P, and delta F2 delta P is equal to Q. These are the equations regarding F2. Now you find the values, two values, and you get P is equal to Q cos omega T minus P upon M omega sin omega T, and Q is equal to Q sin omega T plus P cos omega T. You can do these calculations very easily. Now, if with the help of these transformation equations, these are the transformation equations which you can solve easily for small p and q as well. If you calculate your k, then again k is equal to h, and if you find your k, you will get your k to be 0. So my purpose is solved. It simply means that I should not handle this question with the help of f1, rather I should calculate it with the help of f2. But this is a tedious job. This is a tedious job, that because how may I decide that rather I should choose f1, f2, f3 or f4, which is making my k to be 0. Now for that we find the Hamilton-Jacobi theory. Hamilton-Jacobi theory helps us to find to solve my problem in such a way that it gives me a generating function. That generating function is this generating function is used to find the equations of motion, and when the generating function provided by Hamilton-Jacobi theory is used, I get the direct solution of my problem. So to solve my purpose, that is to find a generating function of the type that make my k 0, we use the Hamilton-Jacobi theory. Now what we do in that theory? First of all, we assume that there is a generating function. Let S be a function. We are assuming this function such that S is a function of small q, capital P and T. You know that this is F2, such that it satisfies the equations of motion. That means delta S, delta Q is equal to P, and delta S, delta Pi is equal to Qi. ठीक? Because it is of the type F2, and for F2 it is of the type F2, and for F2 we know that delta F2 delta Qi is equal to Pi, and delta F2 delta capital Pi is equal to Qi. So using these two relations we find these two equations, right? So first of all, you have considered this function such that this is satisfied and this is satisfied. Further, k minus h is equal to delta S delta t. We also get this for F2 or for S. Now, my purpose is to make k 0. I assume that k is 0. Okay. Then 4 will imply that h plus delta S delta t is equal to 0. But your h involves q, p and time, and delta S delta t is equal to 0. In this equation, I may use this relation. Because I'll eliminate all p. H in place of q, I'll put this is qi, pi and t. So qi, then pi is delta S delta qi, and time plus delta S delta t to be 0. Right? Now, if you look at this equation, then in this equation, you already know Hamilton. You already know Hamilton's function h. So this equation 6, in this form, this equation 6 is known as Hamilton-Jacobi equation. That simply means that if in this equation 4 you take k0 or you get k0, you replace small p in terms of the solution S, generating function S, then whatever equation you get, that is called the Hamilton-Jacobi equation. Secondly, this S, which is basically a function of Qi and then Pi. But what is your Pi? You have assumed K to be 0. This means that P dot is constant, P dot is 0 and Q dot is 0. This implies P I is constant and let it be L5. So this S basically is a function of Qi and then some Pi. At this stage I am talking about capital Pi and time. This S is known as basically this is a function of t. Now you can say that this S is a function of, because in this expression you can see that you are having these Qi's. All Pi's are replaced with the help of delta S, delta Pi. So I may also say that the solution of 6, whatever will be the solution of 6, this solution of 6 or the function S, this function S is called Hamilton's function. This is known as Hamilton's principal function. Right? Now you see that in this equation 6, we are having a function S which is depending upon Qi's, some constants and time. Further, your equation 6 is a first order differential equation in which you have n independent coordinates in terms of Q and one independent coordinate time. So you are having n plus 1 independent coordinates in 6. So naturally, whatever will be its solution in terms of capital S, that will be a function of S will be a function of Q1, Q2, that will contain n plus 1 constants of integration. Because your equation 6, you look at equation 6 again, your equation 6 is involving the partial derivatives of S with respect to n independent coordinates. So when you solve this equation, whatever solution of this equation is obtained, that will be a function of n plus 1 constants of integration. So finally, what is your S? S is Q1, Q2 to Qn. Suppose alpha 1, alpha 2, alpha n and alpha n plus 1, these are the n plus 1 constants of integration. Now, here is one interesting fact that you see in equation 6, S is appearing through its derivatives. It is not appearing as such in the form of S, rather it is appearing in terms of its derivatives. So if I take S plus alpha n plus 1 or I add some constant in S, that will also satisfy 6. So I assume this to be an additive constant. This is an additive constant which is not affecting my solution, which is not affecting equation 6. Therefore, I'll ignore this additive constant and I will be with only remaining n constants. So finally, your S is a function of two n plus 1 variables, q1, q2 to qn, then alpha 1, alpha 2 to alpha n in time. These are called the true constants, and this is called the additive constant, right? In this way, we want to find a generating function S in Hamilton-Jacobi theory, such that for this generating function, my pi should be constant, my q, that means my q should be constant, my p should be constant, and so that I may get the solution. How will I get the solution? Suppose I again come to equation 2 and 3. So you look at 3. What will happen in 3? So what is my S relations for S? Delta S delta Qi is Pi, and delta S delta Pi is Qi. You know that Pi constant, Qi constant. Suppose these are alpha i's and these are beta i's. Now you look at this equation, delta S delta alpha I is equal to beta I. And if I come to and from here, because S is a function of Q's, alphas and T, so you will get an expression from here which is in terms of Q, alpha and beta. That means you can say that you get your beta i's as a function of Q i's, alpha i's and time. And similarly, if I take this relation, then delta S delta Qi is equal to Pi implies I get Pi as a function of Qi and alpha I and time, because S is involving Qi, alpha I and time. Now putting Pi's, replacing Pi's by P naught i's, Qi by Q naught i's, I may get from here alpha I in terms of P naught I, Q naught I and T naught. And replacing this alpha I in this expression, I may get my Qi, or first of all I'll get beta I, then by replacing beta I, I'll get my Qi as a function of P naught I initial coordinates and time. So you get your Q in terms of initial coordinates. Likewise, you will get your P. Substituting this Q here, you will get your P in terms of initial coordinates. These initial coordinates are nothing but the new coordinates. These are designated as the new coordinates. And you see, you are getting your equations directly. These are the equations describing your system. So I'll explain it with the help of an example. We'll again go to the dynamical system described as linear harmonic oscillator. So I'll apply the Hamilton-Jacobi theory to a question to get the procedure. The question is a simple harmonic oscillator. For simple harmonic oscillator, I know that H is given by P square upon 2m plus half m omega square q square. Right? This is Hamiltonian. Now what is my purpose? My purpose is, number one, final purpose is to find Q and P transform. And these should be transformed in terms of initial values of Q and P, so that this will be the final solution. Number 2, because I have assumed k to be 0 in Hamilton-Jacobi theory, that means my p is constant, my q is constant. So I'll find s, a generating function or Hamilton's principal function, such that delta s, this s is a function of q and t, such that delta s delta q is equal to p, and delta s delta, because when I'll take the capital P, it will be alpha, is equal to beta. By using these relations, I can find the final solution. So what I do in step 1, I'll find the Hamilton-Jacobi equation. In h plus delta f delta t is equal to 0, assume that s is the Hamilton's principal function, right? And s is a function of q and t. So it will be the solution of it. So get Hamilton-Jacobi equation. How we get the Hamilton-Jacobi equation? We replace in this h all these p by delta s delta q, right? So I'll write this h is p square upon 2m. So in place of p, I'll write delta s delta q square 1 upon 2m plus half m omega square q square. This is the value of h in terms of delta s delta q, plus in place of this delta f delta t, I'll write delta s delta t is equal to 0, right? So get Hamilton-Jacobi equation by replacing p in h by delta s delta q. Okay, so this equation 2, I'll take these as 1, this is 2. Equation 2 is Hamilton-Jacobi equation. Okay, now you see that in this equation, this part and this part is free from q, and the another part is free from, this is free from t and this is free from q. So variable separable technique is possible. So in step 2, we shall write these two like 1 upon twice m delta s delta q square plus half m omega square q square is equal to minus delta s delta t. As this is free from this part is free from t, this part is free from q. I may assume this part as to be alpha, so this will also be equal to alpha. So I assume let 1 upon 2m delta s delta q square plus half m omega square q square is equal to alpha. So what will 3 give? The 3 will provide minus delta s delta t is equal to alpha, or s is equal to minus alpha t. This is one solution of s in terms of t. And you know that in this part s is a function of q. So I'll assume that s to be of this form: w a function of q and then minus alpha t. Take it as 5 and this is 6. So this implies delta S delta Q is delta W delta Q. I'll use this value in 4 and I'll get 1 upon 2n, because my purpose is to find S. My purpose is to find S. So I have to calculate this W. Delta W delta Q square plus half m omega square Q square is alpha. Solve it for delta W delta Q. It will be root twice m alpha square root of 1 minus m omega square Q square upon 2 alpha. Okay. And then we will find the value of W. You can very well integrate it to get W. W is a single variable function. So W is equal to integral twice m alpha square root of 1 minus, you may require this relation, m is omega square Q square upon 2 alpha. Right? So this is your W. So you get your S. Use in 6 and get S. S is equal to integral twice m alpha 1 minus m omega square Q square upon 2 alpha and minus alpha t. This is your S. Now you look at the previous sheet. I'll find delta S delta alpha to get beta. You look at equation 1. So what I do, I integrate this S with respect, I differentiate this with respect to alpha. So I'll write like this one. This is dq. dq minus t, because when you differentiate it with respect to alpha, you will get only minus t. This integral is with respect to q and you have to differentiate with respect to alpha. So both can be exchanged. You can enter this alpha inside the integral. 2m alpha root 1 minus m omega square Q square upon 2 alpha dq and then minus t. You can easily solve it and you can get delta S delta alpha to be, delta S delta alpha will be 1 upon omega sine inverse Q omega root m upon root 2 alpha. You may solve it. Now what is this delta S delta alpha? This is beta. So you get this expression. And finally, by solving this, you will get omega beta plus t. Take this t this side. Then sine is Q omega root m upon root 2 alpha. So in this way, you may get your Q. Q is 2 alpha upon m omega square sine square omega beta plus t. This is your Q. Equation 9. So my purpose was to find Q in terms of initial coordinates. I'll proceed for that. First of all, I'll try to find what is my P. You know that this is also the relation here. This is a relation. Delta S delta Q is equal to P. So now I'll use it. Since delta S delta Q is equal to P, P is equal to delta W. This implies that P is equal to delta W delta Q, because there is a relation between S and W. And what is delta W delta Q? You have already calculated it from 7. So I'll put this 7 and I'll get P is equal to root twice m alpha 1 minus m omega square upon 2 alpha Q square. This is an expression of P in terms of Q. So use the value of Q from 9. From 9, P is equal to twice m alpha m omega square 2 alpha, and in place of Q square I may put Q square. This is Q square. This is Q square. Twice alpha m omega square sine square omega beta plus t. These will be cancelled and you will get cos square omega. So finally P is 2 m alpha cos omega beta plus t. Or you can say P square is twice m alpha cos square omega beta plus t. So these are certain relations. Here your P is in terms of beta in time and alpha. Here your Q is in terms of alpha beta in time. So what we will do, my purpose is to find these P and Q in terms of initial coordinates. So for that I have to find the value of alpha and beta. So you can solve these two equations 9 and 10 for alpha and beta by the simple mathematical procedure. And for that procedure you may find sine square omega from here, cos square omega from here, and then you may add the two. From there you will get some relation. So from 9 and 10 I'll get P square plus Q square omega m square is equal to twice m alpha. If I put P is equal to P naught, Q is equal to Q naught at initial time, then I'll get my alpha as 1 upon 2m P naught square plus Q naught square omega m square. And finally this is the value of alpha. Similarly we can find the value of beta also from the two relations, from these two relations, from 9 and 10. If I divide the two, I'll get 10 square omega, and I'll get a relation like this: 10 square omega. Similarly, its number is 11. Similarly, 10 square omega beta plus t, this will be Q square omega square m square upon t square. So from here you can very well find your beta. Beta will come out to be 1 upon omega tan inverse Q naught, tan inverse first you take in terms of t, tan omega beta plus t is equal to q m omega p. Now again put at t is equal to 0, q is q naught and p is p naught, and solve this relation. You will get beta in terms of 1 upon omega tan inverse q naught omega m upon p naught. So you look at these expressions. You look at 11 and 12. This is alpha in terms of initial coordinates, and this is beta in terms of initial coordinates. Now putting these alpha and beta in P and in Q, you will get your P and Q, small p and q, in terms of initial values of P and Q, and those are nothing but the equations of motion. So it is very simple that you put values of alpha and beta in the expressions of P and Q, and finally you get your description of the dynamical system. So this is all about Hamilton-Jacobi theory, or the use of Hamilton-Jacobi procedure. Thank you so much.